this is a Moody diagram, and we might explore this later, but this is looking at pressure drop being a function of, you look at the equation at the top, of friction times all these parameters. So you see the velocity squared in the numerator. And now this relates to pipe, because piping is a big issue. There's two big issues you deal with fluid dynamics. One is piping and ducts, and the other are flat plates or flat surfaces. Those are the two big issues. So they're really well discerned. And there's a lot of information on this diagram, but what you'll see is the pressure, or the drag, the pressure drop, delta P in this case, is a function of velocity squared. It is. It's also a function of this F value, this friction factor, which you can pull off this Moody diagram. And this Moody diagram is really cool. This is really applied stuff. And I've got an equation on here that can be used instead of this. There's the Colebrook equation and some equations that take this and put it into sort of the form that you can put into a spreadsheet, and you're done for the rest of your life. But so you have velocity squared and friction. Those are the two things I'd like you to note. And then you see in this Moody diagram, it's a bit busy, but you have a laminar side on the left, laminar flow, and turbulent flow on the right. So on the x-axis, you have Reynolds number, which we talked a lot about. This gray area is this transitional area between laminar and turbulent flow, starting at about 2000. And Reynolds number, Mach number, Weber number, all these are dimensionless units. They have no dimensions. And then the friction factor is up here. So you might say, well, laminar is evil. It's horrible. Look how high the friction rate is. Yeah, that's true. But laminar flow occurs at lower velocity. Laminar flow occurs at lower velocity. So low velocity flow has less pressure drag, or delta P if you look at this term. Okay. To see you have the velocity squared term there. So if you want low drag, you want low velocity. That's the end of it. You're done. You don't care about boundary layer, blah, 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 all this stuff. You want low velocity. Well, in the real world, you want to move things often. So that's where this comes in. You want to push an airplane through the wind. You want to push a car through the wind. You want to have air flowing over a heat exchanger to improve convective heat transfer. So you want velocity. And that's where then we look at, okay, what does this mean? Well, we're saying then this laminar, you get these higher numbers because you have, we'll say, this thick, low velocity part of the boundary layer. And then you trip into turbulent boundary layer. And this bottom curve here where it says smooth pipe, see, it goes right up here. That's the bottom one. You get these really low friction rates. And the friction rate goes up as the pipe gets rougher. But you can still see it's very low compared to the laminar friction layer. And that's because if you look at that cross-section of pipe flow, I had another slide, fully developed flow section of turbulent is bigger, while the high velocity component is bigger than the laminar. So there's a lot here. The takeaway from this, I threw a lot of words at you. Velocity squared is always there. Friction rate is always there. Delta P is looking at change in pressure. So that's just a term used in piping where this is often used. So it's talking about drag. Okay. And then we look, here's an equation. This is a real equation you can really use. It's ugly, but it works. You put it in a spreadsheet and you're done. And it's also very humbling because if you look at the exponents, you get 1.85 and 4.86. Those are really weird numbers, but they're empirically obtained. So they're based on tests. You can trust them. They're real. You can spend, as I have, thousands, tens of thousands of dollars designing equipment that you spec based on this equation. And what I really like about it is you can trust it. Like, as you know, you can get all this kind of theory and background and blah, blah, blah. But at the end of the day, you really want to rely on something you can trust. So in real practice, when you do things, at least for me, I try to corroborate these types of things with three sources, we'll say. So for example, if I'm designing something, I'm designing a chair, and I want to cool down the lumbar regions of someone's back. And I think, well, I can do that with conduction, convection, radiation, mass transport, or an endothermic reaction that sucks the heat out. Those are my 5 things I can work with. And so what I would do is I would first look and see what other people do. Then I might ask an expert, and and see what their thoughts are on it. And then I would look at the theory and so on. But I really want to be able to trust several things. So because here we're talking about order of magnitude. I don't want to be off by order of magnitude, like to completely botch something up. So I won't belabor this, but this is just some math. So here we're looking at, this is pressure drop per 100 feet of pipe. Okay, all English units, but super practical. And it's looking at the flow rate in gallons per minute times 1.8 raised to the 1.85 power divided by the friction constant to the 1.85 power. And that's related to the smoothness of the pipe. So glass pipe has a C value of 150, if I recall. Steel is 125. Copper is in between. Wood is lower. So the higher the number, the smoother the pipe is, and you can look that up in tables. And then the pipe diameter in inches. So it's a really easy calculation. So if you have 200 feet of pipe, or 100 feet of pipe, we'll say, and you're running 10 gallons per minute through it, and it's copper, or we'll say it's steel, and it has a diameter of 2 inches, you can just put in those numbers. So steel at 125, diameter with 2 inches, Q with 10 gallons per minute, and you can get the pressure drop. So it's very easy. And this is elevation loss. This, again, just showing you some math that relates to some of the things we've talked about. So if I lift water up 10 feet, I take, so here's 10 feet, delta H, times the density of the water divided by 144. And this is all English units, and I get the pressure drop. It's a really easy calculation, which we're not going to do here, but it's something, again, you can throw in your spreadsheet. Maybe we can go over this sometime, or people are interested in that, because it's so easy. It's really neat. It's a very simple calculation. It makes sense. Density is the weight of the water affects the pressure. If I lift up air 10 feet, that doesn't have as much energy as water. So this is the pressure drop caused by lifting water up. So it's, and okay. And then I just want to show you some of these values too. These are how you handle real fittings. So here we're getting super applied. These are pressure drag issues. So these fittings have weird geometry. And the water, in this case, it could be air, but this is for water, has to flow around nooks and crannies, has to make these turns like in elbows. And by tests, experts have determined these are the losses, and they're in equivalent lengths and that of diameter. So a ball valve, which maybe some of you have seen, that's like it's a ball with a hole in it, and you can get full port ball valves, which basically have no pressure drop. But you have generally a smaller hole that the water would have to flow through. So the pressure drop in that ball valve is the equivalent of adding 6 times the diameter of the pipe. So if you have 1-inch pipe, and here I'm talking about theoretical, not 1-inch nominal, having that ball valve in there is like adding 6 inches there. Pipe is very, very efficient. That's why your blood vessels are pipes. To move energy from point A to point B, you can really do it with no greater efficiency than using a round pipe. That's the way it is. That's why they're all over the place, including inside your body and in plants and everything else. So an elbow, the equivalent loss is 30 times the diameter. So if it's, I said that wrong. If you have a 1-inch pipe, not 10 feet, so a 1-inch pipe, I'd multiply it by 30 is equivalent to 30 inches of pipe, not 30 degrees. Okay, and then the T, that's the run of the T. So you have an outlet of the T and a run of the T. So outlet is the part that goes straight through, or the run is, the outlet is the part that makes a 90-degree angle. So the run of the T, which is, wouldn't think would have much of the pressure drop, it's equal to 20 times the diameter of the pipe. And this is for, now we're looking at air, looking at ductwork. And this, you can look at the velocity. And again, you don't need to know this per se, but I think it's fun to look at these numbers. So this is feet per minute of velocity. And here's the pressure drop based on this geometry. So if you look at this shape on the top versus the shape on the bottom, which is made out of segments, if you look at the 900 feet per minute, this has a pressure drop of 0.01 inches of water column. I know that's an old-fashioned measurement, but that's what's used. When it's segmented like this, it's rougher, and it's twice that pressure drop. It's 0.02, just because the geometry is more clunky. And these are actually values that you use. This isn't some textbook thing. These are values you use for calculating pressure drop in pipes. So the only takeaway from this is This is easy. Right, it's easy to do. You just got to know where to find this information. Now, I've got something a little more elaborate. This is a bit uglier, but this is looking at the ratio of velocities. So you've got a flow into, this is a duct work with an outlet here and a run here. So this is going down the main duct work in your house, and this is making a turn into your bedroom. Well, the flow through the run is very efficient. And that's this chart down here where it says main coefficient, and it looks at the change in velocity. And if the velocity of the inlet and the outlet don't change very much, this is very, very efficient. And anyway, these are multipliers, these C values. Over here, you look up the ratio of velocities and the ratio of flow rates, and you just look up these losses and you calculate them out. So again, I don't want to belabor that, but I just want to show you this is tabulated. And I'll show you another. This one here actually has an extractor, and you can see how it's got the turning vanes or the extractor. So these numbers down here should be lower. Yeah, you see these numbers are bigger. So if you look at this, if you're trying to get air out of here, air hits this turning vane or extractor, and it makes it turn. Okay. But there's a bigger loss going this way because you got this sheet metal in the way. So if you look at these numbers up here, like even the top one, 0.58, that's the loss making this turn. Now, if you compare it with this duct that doesn't have the turning vane, the loss is almost double. It's 1.03 because air does not want to make that turn. It doesn't want to make that turn. And the C values, these should be lower. 0.35 versus 0.8. Wow, big difference. Okay. That's extreme. Zero ratio. So I can't see past it. 0.02. 0.1. Okay. Okay. So you can see these numbers are quite a bit lower because there's nothing to get in the way of air flowing straight through. And then, won't belabor this, but this is how you use these numbers, and you plug in these C values, and you do some simple calculations to calculate these pressure drops. So what this is doing for you is it's saying, based on the geometry, we're going to put in tables what the pressure drop looks like. So it's just sort of applied. This is cost issues, and this, if you are trying to, this relates to sustainability. If you're trying to run something efficiently, and we'll talk about water pipes because you're most familiar with those, or talk about blood veins if you want, arteries. If you make them big, you can run everything at low velocity. So if I want to move water from point A to point B to do heating or cooling, I can use big pipes and I can push the water slowly. And if I push the water slowly, my velocity is low, my drag is low, everything's good. Okay, but there's a downside to that, and that is you've got these giant pipes, and there's a thing called embodied energy associated with that. Big pipes are expensive to make, they're expensive to transport, they're expensive to install, they're expensive to support. So there's an optimization you can go through where you look at, okay, what's the best size to move things efficiently? And this could be a moving target. There's an economics in here because you're saying small pipes are efficient and they're easy to install and easy to make and use less materials and et cetera, et cetera, et cetera, but they require more pumping pressure for the life of them. So this is another example. This is, I probably won't go into this right now, but this is looking at a piping system that is not round. It's actually corrugated. It's got these ripples in it. And you can simulate that as a round pipe. You get this, and I just real quickly here, because I do want to talk a little bit about rheology, and then we'll break out in a few moments. This is, so you take data, actual measurements, and you convert it to an equation, okay, which I did here, and you put it into a spreadsheet, a program, or whatever, and it solves. So this whole issue with drag and pressure drop is surprisingly manageable. My dream for you is that you're not intimidated by it at all. In other words, we're looking at sort of theory. I just threw some practical examples of how it's really used. As designers, when you're designing something, you're trying to think about drag, and you're trying to think about pressure drops and heat transfer and these kind of things as you're doing it. You're not trying to do those sort of mathematical equations, but if you're pushed into it, you can do it, and you do it by standing on the shoulders of the giants, and it's all out there. In fact, there is a, like we looked at computational fluid dynamics, there's computer modeling that's available too. And I'm going to, well, I'll talk about some of that at the end of this. Okay, so just for a few moments, I want to talk about rheology. Just